topic of program of this quantum groups. It's my great pleasure to say that the lectures on this topic will be given by Professors Brannan and Mateusz Wasilewski. Mateusz will start the first lecture.
Yes, thank you very much. Thank you for the invitation. It's a huge responsibility, so I hope there will come great power with it as well. So the rough outline of this maxi course on quantum groups will be, we'll start with some today. I mean, maybe even before lunch, we'll do motivation, basic definitions, and some examples. Then after lunch, more examples. Then tomorrow, Mike will give talks about representation theory of quantum groups. Then then I will come back and I will delve deeper into representation theory, and then I think in the last two lectures will be delivered by Mike, and he'll get to more advanced topics. So for motivation, okay, so I'm an analyst, so I need somehow an analytic motivation. So the motivation that I will give you today, which is maybe not the motivation for everyone who does quantum groups, will be coming from harmonic analysis, so like duality, contracting duality of groups. So what is that? And like basically the Fourier transform. Okay, so the Fourier transform. Okay, so this is this map, say from some sort of functions on R into functions on R. To be more precise, I mean, you can choose different classes of functions. You could do like go from L1 of R into continuous functions vanishing at infinity on R. You can go from L2 of R to L2 of R.
This is less fun.
Slightly less fun, yeah. Okay, and then the most important property of the Fourier transform is that it maps convolutions into the usual product of functions. Right, and so what it means is that you can basically, using Fourier transform, you can transform all the convolution operators into multiplication operators on the other side. Right, and convolution operators are precisely the translation invariant operators, so basically operators invariant under the group action. So if you have a group, then you can look at the operators invariant under the group, or maybe equivariant under the group multiplication by like right or left translations on the group, and then you can study them via Fourier transform, at least if you are on R. Right. So the other case is maybe if your group start with the unit circle, so then you get Fourier series, right? So then from if you have a function on L1 of t, then from this you get f, say, sort of equal to its Fourier series. So this is the okay, so then here if you start, in the first case, if you start from functions on R, after the Fourier transform we will still have functions on R. In the case of the unit circle, right, so these are like the complex numbers of absolute value 1. Then on the other side, this is indexed by Z. So basically we can write a statement as a sort of duality that the dual of R is R, and the dual of the circle is Z. And then the Pontryagin duality is this general statement that any sort of nice abelian group admits a dual, and you can do Fourier analysis there. So Pontryagin duality . So any, and then the correct adjectives will be locally compact abelian group G admits Pontryagin dual G hat, and then there is such that if you do this procedure twice, it's really a duality. So Pontryagin dual will also be a locally compact abelian group, so it will be all the same type. And if you do this operation twice, you recover the original definition. So it's just like, for example, for finite dimensional vector spaces, you take the dual and then take a double dual, you get the original thing. Or as we saw for polynomial algebras, you take the commutant, take the double commutant, sort of, yeah.
Why does it have to be compact?
Doesn't have to be compact, it's locally compact. So it's like a nice assumption. So for example,
Yeah.
so then there's no harm measure on it. So we can't really do analysis on, like you cannot define these like L1 spaces, L2 spaces if you don't have a measure on your group. And it's basically, there is a harm measure on a topological group if and only if it's locally compact. So yeah, you kind of need this assumption. Yeah. Okay, and this Pontryagin dual, I mean it's a concrete object. So what's the Pontryagin dual? The letters are big enough, I hope. Okay. So Pontryagin dual by definition is the set of maps from G to T, and these are group homomorphisms. And then you can endow it with whatever topology you typically put on maps, like a compact open topology or like uniform convergence on compact subsets, things like that. So one of the typical topologies you put on spaces of maps. And then this is a nice exercise to so now this statement here becomes an exercise. But if you look at homomorphisms from R to T, they're actually indexed by R. You can identify them with the group R. Okay, and then so you have this very nice thing for and then there is an analog of the Fourier transform. So there's from functions on G, you can produce via Fourier transform functions on G hat. And then natural question, I mean this works for abelian groups. So what happens for non-abelian groups, right? What happens for non-abelian groups? Well, you can always form this thing, right? This Pontryagin dual, but it just can be very small. Like for example, if your group is, I don't know, like a nice finite group, like permutations on, I don't know, 4 elements. So for the permutation group, there is only 2 homomorphisms to the unit circle. One is somehow the trivial one, where you map everything to 1. And then the other is the sign of the permutation, right? So if it's even, you map it to 1. If it's odd, you map it to -1. So for G, then somehow G hat has only 2 elements. And part of this story here is that on the level of the L2 spaces, this is a unitary transformation, a unitary map between Hilbert spaces. So the thing is that you can go back from G hat to G, right? This is also part of the Pontryagin duality. If you go from G hat, you can recover G as well. And here, G hat will be much smaller than the original group. So you need a bigger object somehow. And as I said, this Fourier transform basically diagonalizes convolution operators. And convolution operators, this is something that still makes sense on a general group, right? You can, locally compact group which has a Haar measure, then you can form convolution operators. So analog of the Fourier, the analog of the Fourier transform is basically the left regular representation. So what's the left regular representation? So you start from function on, say, an integrable function on your group, and then from this you form an operator, lambda f, and this will be an operator on L2 of your group. And how does it act? So lambda f on some other function h, you just convolve h with f from the left. And then you can look at von Neumann subalgebra generated by these operators, these left conversion operators on this Hilbert space. And then in the abelian case, you could really identify this with some functions on the dual. So yeah, let me maybe make it slightly, maybe let me just write down something. So L of G, this is the group von Neumann algebra. This is the weak operator topology closure of this set lambda f, where f is in L1 of G. Okay, and then if G is abelian, then L of G can be identified with L infinity functions on the Pontryagin dual. Right, because these are convolution operators, and convolution operators via Fourier transform become multiplication operators, so functions really on the dual. That's the whole point. Okay, so now if you want to extend Pontryagin duality, somehow have this sort of group-like object which is dual to original G, then sort of L of G will be a replacement of that in a way. And somehow the idea behind that is this Gelfand duality. So this is something from C-star algebras, right? So C-star algebras are these star subalgebras of B of H, which are closed in this, the bad topology from Robin-Stokes, right? So the norm topology. I mean, I agree. I also prefer von Neumann algebras, but sometimes you have to work with C-star algebras. So C-star algebras are star subalgebras of B of H closed in norm topology. And for this motivation part of the talk, the important class are the abelian C-star algebras. So so say X is a compact. So what's the convention? I should add Hausdorff if I assume it's Hausdorff, right? It's not automatic with compact. Okay, so compact Hausdorff space. Okay, then C of X is a C-star algebra. Right, and this is roughly like in Robin-Stokes for the L infinity of X. When you find measures on X, and then C of X acts on L2 by left multiplication. So you can review it inside some B of H. Okay, and then what is nice about the C of X is somehow it knows everything about X. So basically the thing is that if you have two spaces, X and Y, then there is one-to-one correspondence between functions from X to Y and star homomorphisms from C of y to C of x. So star homomorphisms are maps that preserve the product and also the adjoint, right? And how does it work? I mean, if you have a function from x to y, then if you start from function y, you compose it with this original function and you get a function on x, right? So, and the other way, I mean, this is somehow part of the Gelfand duality. There is like an analog of the Fourier transform called the Gelfand transform, and this is what you need. So it's not an obvious statement. You need some tools to prove that. But Unital, yes. That's correct.
When you say function, you mean continuous function?
Continue. Yeah, that's why I write C of. Oh yeah, functions. Yeah. If there are like morphisms in the correct category, so if there are compact Hausdorff, it's topological space is natural to have. Yeah. Thanks for. Yeah, try to, somehow in this motivational part I will probably not be super precise at times. And later probably as well. Okay. So then, sort of, this isomorphisms, I mean, this is really fundamental, but it's morally similar thing. So at infinity of G hat, these are also like sort of functions on G hat. So then, basically, if there is a sort of G hat, if there is a dual object, it should be we should be able to identify it using this algebra L of G. And then, so now imagine a G hat exists such that we have this isomorphism. That is really an infinity of some G hat, and then we would like to put some sort of group structure on this object L of G, right? So G hat is the group, means we have a multiplication map. Okay, so then if you have a map between topological spaces, by this duality it should correspond to star homomorphism. Yes?
Do we just any local compact G now, or we still take Z?
Now G is locally compact, probably even better stick to maybe, you can do discrete or compact. I will mostly focus on discrete and compact. Yeah, but this, here G is locally compact, but specifically I want to non-abelian. And somehow, and this is an imagined object, so for now. Okay, and then in this imagined object you would have a group structure, and this would correspond to star homomorphism, which we'll call delta. Well, we should go from an infinity of G hat and G hat, but then this algebra, you can identify it with a tensor product. So what's the tensor product of von Neumann algebras or C-star algebras is you have, say A is inside B of H, so that would be one C-star algebra, von Neumann algebra. B would be inside some other B of K. Then you get A tensor B, so this is like just the algebraic tensor product. So will sit inside operators on H tensor K. H tensor K. And then if you want to do it for C-star algebras, you would take the norm closure of this and obtain a C-star subalgebra. For von Neumann algebras, you would take, any of the closures that Robin described to obtain a phenomenal algebra, and then you get this thing. So it means that you should have, so it means that we should have aside delta going from L of G to L of G tensor L of G. And then also a multiplication map on a group. I mean, it's not just any map from the product to G, it should be associative as well, right? Right. And then associativity of the group multiplication should correspond to a thing that we call co-associativity of the co-multiplication. And then, yeah, then I will have a cheat sheet of this definition here. So co-associativity. So, yeah. Associativity of delta. So this is if you do the delta once, and then so you're in the tensor product, and then if you want to apply the delta second time, you can either start like on the second leg of the tensor product or on the first one. And the co-associativity tells you that you should get the same result. Okay? And then what is this map? So in this specific case, we have this map. So delta is the extension of the map, yeah, we define on these shifts. So this is just shift by a group element G, and on these elements we define that this is lambda G tensor lambda G. Okay, so yeah, we have a candidate for the analog of a multiplication. It should be the sort of thing that we'll call co-multiplication, which should satisfy this co-associativity condition that's here on this board.
So in the line above, you want the completed tensor.
Oh yeah. Yes. Okay, so this is the, yeah, but then this is just a multiplication map, so that's not yet a group, that's a semi-group, right? So normally for a group you also have a unit and you have the inverse. Okay, so like if, so no, I don't want to move here yet. So analogs. Of inverse and the unit. So these are things called antipode. So one is the this is as, yeah, just define them on this linearly dense subset. So we have this. And then we have the co-unit. This is, yeah, I remember this is, I think, always one in this case. So we have these things, and then maybe I should write what these maps S and epsilon and delta are for a classical group, right? So if you still have a group, not really like the dual of a group that doesn't exist, but an actual group, what are these maps? So delta, S, epsilon for classical groups. So what it means is that we work with the continuous functions on G. Then what is delta? So maybe, yeah, for simplicity to have things unital, we assume G is compact. Then we have this delta from C of G to C of G tensor C of G. And how does it work? applying delta of f. So this should be a function of two variables, right? So at points gh, well, this is just f of gh. The s on f, I mean, this should be the analog of the inverse, right? So if you take s of f at g, it means that you should apply f to g inverse. And the last one is the counit epsilon. So epsilon will be just the evaluation. So epsilon of f will be just evaluation, at the unit. So where does this, so S is a map from C of G to C of G, and epsilon is a map from C of G to C. And basically we can, we can axiomatize what these maps should satisfy, and this can lead us to a definition of some type of quantum group. So what are the axioms? I mean, I can write them down. I will write them down here. Okay, so the antipode should satisfy. If we do first multiplication, or co-multiplication, then so it's the same. Okay, so this m will be the multiplication on our algebra now. Yeah, that's not good. Maybe I write mu. So mu is the multiplication map on our algebra. It's like you do the multiplication, so you have this gh, then you invert one of the elements, so you have like g inverse h, and then this multiplication is taking the diagonal in a way, so like evaluating this function of two variables at the same arguments. So it means that you would have h1 times h, so it means that you evaluate at the unit. So this should be equal to the co-unit times 1, and it's the same in the other direction. And the axioms for the co-unit are that the co-unit is like, so if you do multiplication and then you basically set one of the variables to be the unit, it means that you don't do anything. And the same in the other direction, right? If you multiply from the right by the unit, it means that you haven't done anything. So then one might be tempted to define, say, like here I assume G is compact. So to define a compact quantum group to be a unit Alcista algebra equipped with this sort of maps delta, S, and epsilon, satisfying these axioms, and they should be nice maps on Cista algebras, so maybe star homomorphisms. And there are some problems if you try this approach, and these problems are all, basically all of them are seen in this famous example of Voronovich. So like the SUQ2 quantum group of Voronovich. So if you ever see some introduction to quantum groups, this is probably the example that you will see. And how does it work? So we want to have a system algebra, which will be our analog of C of G, and you want to have the structure maps. Okay, so what is the system algebra? So system algebra of SUQ2 is generated by two elements, alpha and gamma, such that the matrix do alpha, alpha star, gamma star is unitary. So what I mean by this is that it's a system algebra, so C of SUQ2 will live inside some B of H. Then this operator matrix, this will live in B of H plus H. So it will be a nice operator on the Hilbert space, and you ask this operator to be unitary. Okay, and what are the maps?
What's the value of Q? So Q is
Sorry, yeah. So Q is between -1 and 1, but not 0. Yes. And maybe it makes sense. Yeah, this matrix is, yes, I call it U. Rewrite it. Q gamma star, gamma alpha, alpha star. And then basically the co-multiplication is the dual of the matrix multiplication. So you like view it. This will be like an example of what is so-called matrix compact quantum group. So it's just like if you have a Lie group, say SU2, then all of functions on the Lie group are like, you start from polynomials in the matrix entries of the UIJs, and then you take the closure. This will get you all continuous functions. And this is somehow analogous to that. And then the multiplication is matrix multiplication. So what is nice about this setting is that the matrix multiplication is automatically associative, which means that the co-multiplication, if we can define it, is somehow automatically co-associative. We don't have to check it extra. So what is the delta? So the formula is not really to see the analogy with the matrix multiplication. So on Uij, which is one of these entries, will be sum over Uik tensor Ukj. So to make it precise, we have two generators, alpha and gamma. So the value at alpha will be equal to alpha tensor alpha minus q gamma star tensor gamma, and delta of gamma will be gamma tensor alpha plus alpha star tensor gamma. So this is really, this formula somehow applied in these specific cases. So I think that if you first see these formulas, they just seem as like random formulas. So maybe it's better to start from this general formula, which just reminds you of matrix multiplication, and then apply it to this specific example.
What is this H you're appealing to?
H here? I mean, this is some representation, some faithful representation of your system algebra.
You want to leave it
I don't want to. I mean, I will now give an example of H, actually. Yeah, because that leads me to this is somehow very good comment, because it leads you to a natural question. Okay, you say you want to consider system algebra generated by some elements satisfying some relations. You actually don't know if it's like trivial or non-trivial. It may be very small. You don't know, right? In principle, unless you find a nice representation. So maybe first I will finish writing what are the structure maps in this case. And then, yeah, I will show you this representation to somehow, yeah, that confirms that this is a non-trivial example. So the antipode. So once again, if you compute it for the, for the classical case where you have an actual compact group and you have this formula, then in terms of the matrix entries of your group, you arrive at this formula that S of Uij should be Uji star. This is just the formula you get for the matrix entries. Okay, and then what does it give us in our case? It means that, okay, so alpha is the 1,1 entry. So S of alpha should be alpha star. Right, because it's the same entry, but you apply this, you get the star. So S of alpha should be alpha star. And then S of gamma, I mean, this is the 2,1 entry, so you should get the 1,2 entry and take the star. So S of gamma is minus Q gamma. Okay, and this already shows the issues with with this nice approach that we thought would work. Is that there is no chance that this S will extend to some bounded map on our C-star algebra. Because, I mean, yeah, you can do somehow this opposite thing, like use gamma star, and then you will get an eigenvector with eigenvalue bigger than 1, like 1 over q. And you can apply it, I mean, it's a multiplicative map. It's supposed to be multiplicative, so it gets that S of, gamma star to the power n will get growing eigenvalues to infinity. So there is no hope that S extends to an actual bounded map on our C-star algebra. S cannot extend to a bounded map on the C-star algebra of SU Q2. I mean, unless Q is 1 or something, which is the classical case. Yeah, this is maybe something that I should have said. Like if Q is 1, you recover the classical SU2 group. So then things work nicely. But as soon as Q is strictly between -1 and 1, yeah, things somehow start diverging.
So I still have a question. So what does it mean that this matrix is here?
I mean, it's an operator here, so it means that this operator in B of H satisfies that U star U is equal to U star is equal to the identity operator.
And the star is just the star like you would to the
Yeah,
matrix.
exactly. Yeah. So it's like so the star is here. You do transpose, and then the conjugate is taking the star. Yeah, so
What is the identity of the matrix?
just 1 1. Yeah. Yeah. So identity would be identity on H, identity on the other copy of H, and zeros also. So maybe I can. Okay. How many? 2 minutes. Okay. So this will be So I will just write the explicit representation to wrap things up. So explicit representation. So you want to find actually operators alpha and gamma on some Hilbert space. So that would satisfy these properties that if you form this 2x2 matrix, it will be unitary. So what's your Hilbert space? H will be L2 of, you take non-negative numbers here and take the product with Z. So this has a natural, nice orthonormal basis indexed by just by this set. And then you define alpha on E and K. So this will be the weighted unilateral shift. So we put this Q somewhere with some power, and then you so it means that this is 0 for n equal to 0. Somehow when you shift to -1, it means that you're 0, so it's a unilateral shift on this variable, and then gamma on E and K is Q to the power n E n K plus 1. So this is shift on this Z part, so it's a bilateral shift. So it's a slightly nicer operator. And then you can check that with these operators, somehow the defining relations of this C-star algebra FSEQ2 are satisfied. Okay, and I think you deserved lunch.
For lunch, do we have any comments or questions?
Yes?
Maybe a bit technical, but this tensor product of von Neumann algebras, I was just wondering, like in the C-star algebra case, are there multiple choices in the von Neumann algebra setting for the tensor completion?
Not really. I mean, no. Like if you choose inclusion into P of H, it's really, and you just take the weak star operator closure inside the tensor product. It's always the same thing, regardless of the representation. But I mean, you can. Yeah, I will not go into deeper details.
This also happens for
C-star algebras, right? If you choose two.
Yeah, that's true. Yeah, that's true. For C algebras, I mean, this what is called the minimal C-star tensor product of C algebras. So this naive one. Yeah.
Mr. Brannan wants to.
Oh, I was just curious what epsilon is for this. No.
I didn't write it down. No. Forgot. So epsilon is. Epsilon on Uij would be delta ij. So then, yeah, for each entry you get something.
So maybe still one short comment to the question asked before. So, see, like in the lectures of Robin, von Neumann algebra came with a Hilbert space. He said it's really realized in B of H. So this is a big difference. I mean, this C-star algebra. So here Mateusz wrote H, but okay.
I didn't say what it. Yeah, it's like. Yeah, it's like it's an object. Like a C-star algebra is an object on its own, and you can embed it into different Hilbert spaces possibly.
So this is the difference.
So this is more of a comment, but so the axioms you've written down for Hopf algebra,
More or less, yeah.
and in the compact functions on a genuine, sorry, continuous functions on a genuine compact group do seem to work. Can we do that at the von Neumann level, or are there already problems with topology?
I mean, like evaluation at the unit, for example, it's tricky. Yeah. That's why, yeah, the motivation part is really not very precise. Just to see what should be the objects roughly, but not really caring about the details yet.
Okay, so let us thank Mateusz again.